Good afternoon, I'm Mr. Rich. Thank you for joining me. A good video, a relatively interesting video because we're looking at the prediction of strength of organic acids. A question or two of these might creep up on an exam, especially in high school chemistry. It doesn't matter if it's the AP chemistry exam or another exam similar to that, but something like this can show up. What do we talk about here with regards to organic acids, or what are organic acids? Well, they're certainly not these, the mineral acids. HCl, HNO3, H2SO4, these are your mineral acids. We're talking about organic acids which are based around the carbon molecule. You know, carbon has a valence of 4, it is C6. When you look at it, 1s2, 2s2, 2p2, you're looking at the 2s orbital and then the p orbitals. It looks like these. In terms of electrons, you have 2 here and then you have 2 here. These 4 electrons are your valence, and carbon will always have at least 4 bonds around it. And you have to keep that in mind when you're looking at organic chemistry, and the valence of 4 comes into play. We have to keep everything here general because we're not talking about organic chemistry, we're talking about high school chemistry. We have methanol, ethanol, water, acetic acid, and benzoic acid. I'll just spell this out here. This is benzoic acid. Each of these acids or potential acids are written here from weak to strong. I've just put water here as just a reference. Our main topic here is these two and these two: methanol, ethanol, acetic acid, and benzoic acid. Water, you know, can serve as an acid and a base because it can accept a proton, it can give a proton, it has that quality. But these are more bases than they are acids. I'm only utilizing them here in this representation only because they have the potential to act as an acid. This right here is from weak or not acid at all to strong. But all of these, especially these two here, which are much stronger than those, are still very weak compared to those mineral acids I showed you earlier. Anyhow, what would be representative reactions over here? You'd be always generating a conjugate base and a proton. This is why, by means of this reaction, even though these are not acids, they can behave as an acid. And of course, here you'll have this CH3, CH2O-, and then H+. Not very likely to happen at all. The reaction will more likely exist towards the left. These ones here you can see will form the acetate anion, the acetate, and then you will have that. You'll have a oxygen here with a negative charge. Here you'll have the benzoate anion. These have the ate suffix, ate. Benzoic became benzoate. Acetic became acetate. Anyhow, here's our compound right over here, and then H+. How do you predict the strength of these organic acids? It's by means of not what you're looking at over here, but by means of the conjugate base. And the tip I'll have for all of you momentarily will be with regards to what you see right here. All of these items I'm putting in a box is what you really focus on. That right there is where the money lies, as they say. If the conjugate base, which I'm abbreviating as this, is stable and it's a weak base, then it will be coming from a strong acid. Alright, keep that in mind. It will come from a strong acid. If your conjugate base is stabilized and it's stable structure, but it's a weak conjugate base, it's coming from a strong acid. If your conjugate base is less stable, alright, less stable, and I'll talk about the stability momentarily, and it's a strong conjugate base, and I'll abbreviate that, strong conjugate base, then that conjugate base is coming from a weak acid, or let me say this, non-acid, because it could be coming from a compound that's not even acid to begin with. These are not really acids at all. So keep that in mind and think about it again. If the conjugate base is not stable but it's a strong base, which these are strong bases, because think about bases as something wanting to accept a proton. These really want to accept that proton and go back over here. If your conjugate bases are less stable because of that negative charge on the oxygen, but they are strong conjugate bases, they're coming from compounds which are weak acids, or they may not be acids at all. If your conjugate bases are stable because of something called resonance, which we'll talk about soon, resonance in this video, but soon, resonance, then these are conjugate bases which are relatively weak, and they're, in terms of basic character, they're weak bases, but they're coming from atoms or compounds which are strong acids, which is why these are strong acids and these are non-acids, or they're very weak acids. You have to remember this for your prediction of organic acid strengths. Now, let's talk about resonance. These compounds here are not stable because they don't have resonance stabilization. These compounds here are stable because they have resonance stabilization. Resonance stabilization is the ability of a compound to spread that negative charge or even a positive charge. Here we're looking at negatives only, to spread the charge over the compound. As you spread that charge over the compound, you increase the stability of that species or that anion or even a cation. But by resonance stabilization or the resonance effect, you're increasing the stability of the ionic species that has developed. Here you don't have resonance, so these are less stable and they want to go back. Here you have resonance, these are more stable. They'll still want to go back, but they won't have that much of a desire to go back, or they could relatively persist in this form for a while before they head back in the original direction. Let's talk about resonance stabilization. I told you this CH3O minus coming from the methanol and the CH3 CH2O minus coming from the ethanol, they don't have resonance, so these are less stable and therefore they're not coming from compounds which are acidic, so these are less stable. Our remainder of the video will pertain to these compounds right here which have resonance. Let's look at these acetate. The acetate anion has resonance stabilization because this negative charge can spread out to another part of the compound and it can look something like this, C, and then here you got O, and then here you have minus. You see the difference between this and this? Here I have a double bond to the oxygen on the top, here I have a double bond to the oxygen on the bottom. Here I have negative on this oxygen, here I have negative on that. But this right here is resonance stabilization, and there's two structures which can spread that negative on the oxygen and make this stable, and therefore this conjugate base will be a weak base, but it will be a stable conjugate base coming from a compound that was acidic. When you look at the benzoic acid, it's a little different. You see how before I was using something like this? That's just a shortcut for representing benzene, which looks like that. There are 3 double bonds in benzene and it looks like these. And these are double bonds. But anyhow, benzoate. Now when you want to spread this out, there are many structures you can spread it out, but we won't show you all the structures because that's organic chemistry. I'm only showing you a few structures, but you'll see there are more of these. Benzoate has more resonance structures than acetate, which is why benzoate, the anion, is more stable. Therefore it's coming from a compound that's more acidic. Benzoic acid is more acidic than acetic acid because it has more resonance structures. And a resonance structure can be something like this. For this compound, it could be like this. You see how I have this and I have this slight difference. Another resonance structure can be exactly what I'm showing you right over here, and keep an eye on what I'm doing. I have exactly the same thing as this, except now I'm shuffling around these bonds. And there's another resonance structure. Now look at what I'm doing over here. I'm doing the exact same thing. I'm keeping exactly what I have over here. Right over here. I have the negative over here, but I'm shuffling around these double bonds. I've already gotten 4 resonance structures. I'll add one more before I'll stop. One resonance structure can be also this. Look what I'm doing here. Right there, that's another resonance structure. There are 2 resonance structures here. There's 1, 2, 3, 4, 5, and there are more. But they're already more than acetate. Therefore, acetate is coming from a compound which is weaker than benzoate, which is coming from a compound which is a stronger acid. So keep that in mind. Even among the strong organic acids, the ones which have more resonance structures will be stronger acids because their conjugate bases will be more stable. This right here is a good acid, but it's less of an acid than this because this has more stability in terms of its conjugate base. So what's your take-home message for organic acids? If the conjugate base, which you know brings an oxygen with a negative charge, if it can be stabilized by means of resonance structures, which I'm abbreviating as RS, then it's coming from a compound which is a strong acid, I'm abbreviating. If your conjugate base from an organic compound is stabilized by means of resonance structures, it's coming from a relatively strong acid. But remember, all organic acids are much weaker than mineral acids. If your conjugate base coming from an organic compound has no resonance ability, no resonance stability, no resonance structures, then it's coming from a compound that's not an acid, organic acid, or it was a very, very weak organic acid. But then those conjugate bases will be very strong bases. These conjugate bases will be weak conjugate bases. So keep that in mind. A weak conjugate base means a strong acid. A strong conjugate base comes from a weak acid. And that right there will bring us to the end of this video. Thank you.